this maths video. In this video, I'm going to be talking about algebraic geometry, and I'm going to be talking about sheaves. And of course, this is part of my learning algebraic geometry series, where basically I'm going to be going through vakil, and I'm going to just be recording my learning and whatever on this board right here, every week basically. Now, obviously, this was like not first week, but like second or third week back from school. So, you know, I'm properly back in school now, and, you know, teachers are actually giving homework, so of course, you know, I can't afford to spend that much time getting through the book. So, of course, I'm not going to say, oh, every single week I'll do X amount of subsections or whatever, because, you know, I might have a holiday where I might be able to finish like a whole section, or and then I might have a week where I just do like, you know, one subsection. So, you know, really vary. And this week I did the first two subsections. Now, the first subsection was just a motivating example of sheaves, and I've already recorded a video wherein I talked about the motivating example. I didn't really motivate what a sheath was, so I'm just going to completely omit that and maybe just give it as an example of a sheath instead of using it as motivation. If you really want motivation, then watch one of those motivational speech videos on YouTube. Okay, so I'm just going to go straight into the definition of a pre-sheath. So definition. A pre-sheath, which we'll denote by this weird math script F, is a controversial. Now, I could define it slightly. Sorry. Pre-sheath F over some topological space X. Sorry, a pre-sheath of rings, or no, actually of sets. We could replace this with groups, rings, any kind of category, appropriate category, but we'll just call it sets now. Pre-sheath of sets over X. Now, I could define this a little bit more ugly, but this is just a nicer way of defining it. Pre-sheath F of sets over X is a contravariant functor from the category of open subsets of X, which I'll denote by open X, to, and in this case it'll be set. Again, just replace that with any category. Now, what this category actually is, it consists of objects being open subsets, morphisms being inclusions. So, what the pre-sheath is it associates to each open subset of X a set F of U, and to each inclusion it will associate to it a restriction, so contravariantly. So let me write that out explicitly. If we have an inclusion U being included into V, this then, you know, this is then inducing a map. Sorry, going the other way. And this is denoted by res VU. So, okay, so it goes the other way. Of course, by the fact that it's a contravariant functor, if we add in another guy, if we add in a W, and we have, you know, maps going like this will commute. And basically what this is saying is, if you restrict a map from W all the way down to U, that's the same as restricting it to a medium-sized open set and then to a small set. So that's all this commutative diagram is saying. So that's what a pre-sheath is. Let's take a look at what a sheath is. Now, a sheath adds on to this two slightly more technical axioms. Okay, so definition. A sheath. A sheath, which again we'll call F, of sets over some space X, is a pre-sheaf such that firstly we have that the identity axiom holds. So we have the identity. So the identity axiom says that, let's say we have an open cover UI. Of U. Then, if the restriction of F1 to E, which is where F1 is a section over U, that is, it's an element of this F of U, it's just called a section over U. If the restriction of some section over U to every single open cover is equal to the restriction of a different section over every single open cover, every single member of this open cover, then this meant that the two functions were the same. So if they agree when you restrict them to each of these open covers, then they will agree globally. And gluability, what's gluability saying? Gluability is basically saying if you have two functions defined on different sets that agree on the overlap, then somehow they can be glued together in a certain sense. So more precisely, if again UI is an open cover view, if the restriction or so now we have a function defined on one of these UIs. The restriction of UI to UI the restriction of Fi, which is a section over UI, to the overlap between UI and UJ. So, okay, I'll just write it out. So basically, these two functions, this one is a section over UI, this one is a section over UJ, and if they agree on the the intersection or the overlap of UI and UJ, then you can somehow glue them together, basically. Then there exists some F, which is a section over U, such that the restriction of F to UI is equal to Fi for all I. Okay, so now, before I move on to any examples, I'm actually going to take a quick look at a very, very mind-blowing categorical perspective to sheaves. Now, of course, a pre-sheaf, I've defined it from off the bat categorically as a contravariant functor. But these two extra axioms can be interpreted via a certain equalizer diagram. Equalizer exact sequence is what it's called. So firstly the identity axiom. Let's just replace this res right here with F. This is saying if F of F1, actually no, let's call it G. If G of F1 is equal to G of F2, then F1 is equal to F2. That is very much like injectivity. The only problem is that this UI is arbitrary. And the solution is you just smash them all into one thing by taking the product. So let's look at what exactly this looks like. So we're going to go to F of the union over all of these open covers to the product of each and every one of these things. And the way we get to there is, alright, so let's say we do the restriction going down to one of these things. If we have the projection, let's call it pi I, let's just call it pi, then this map here, I, has to make this commute, and of course the way that I does that is I of some f is going to take it 2, and then each little tuple, so we're going to have f restricted to u1, f restricted to u2, and so on and so forth. And each of these restrictions is going to just be called f1, f2, f3, okay. And that will make the whole thing commute, this little triangle. And what identity now is saying is that I is injective. You can see why this is true, but because if you think about it, this right here is if you do something to f1 and you do the same thing to f2 and that turns out to be equal, then the original two things that you're doing them to is equal. That's just injectivity. If g of x equal to g of y, then x equals y. If res f1 is equal to res f2, then f1 is equal to f2. The way we've made this notion precise is by smashing all of these ui's into one thing, and saying that identity is the same thing as saying that this I is injective, which is true. But we're not done yet. So identity is saying that I is injective. Okay. Next, we're going to keep going, and we're going to rephrase gluability in terms of this diagram too. We'll call this map alpha, we'll call this map beta. Now, okay, what's alpha doing? Alpha of some tuple, we'll call it product over I of fi's, is going to be the product over all I and j of fi restricted to ui intersect uj. And what beta is going to do, if beta takes in the same thing, just some product, then it's going to do the product over all ij, but except this time it's going to do fj restricted to ui intersect uj. Okay? So that's what beta and alpha are doing. And what gluability is saying is if these two, so if we just ignore the product sign for a moment, if these two things are equal, then, yeah, if these two things are equal, then this fi, this fi here, so if we cover up, just imagine this product sign is not here, and this product sign is not here. If these two things are equal, then this fi was in the image of that. So, let's write that out more precisely. So, maybe if I write it out, let's see, if alpha of one little fi is equal to beta fi, which is basically saying that fi restricted to this in overlap is equal to fj restricted to this overlap, then the image, then that means that fi is in the image of I. And this is called the equalizer exact sequence because this means that the image is, okay, let's say we can, now it's not a precise thing at all, but if we're allowed to kind of introduce addition and subtraction, if we have a certain notion of addition and subtraction, then what this is really saying is that the image of I is equal to the kernel of alpha minus beta. These two maps here, because the image of I is precisely the stuff when these alpha and beta are equal, which, and if we're allowed to introduce subtraction, that's just when alpha minus beta is 0. And that's just a crazy, way of talking about these sheaves, these extra two axioms categorically. But to be honest, the only reason I was able to rattle this and that off, so without really having to stop to think about that, is because I do have this type of thing in my head. I've got the injectivity, I've got the kind of intersections, I've got the overlaps in my head, and then that easily helps me to remember. Also, it might be the case that these particular maps, alpha and beta, or this I, might actually be specifically useful in proving something about sheaves. So it's always good to have more than one perspective anyway. So okay, that's all of the kind of like the theory that I've learned. And basically the rest of what I'm going to be doing is some examples. Okay. First example. Oh, crud. Yeah, okay, I've got to talk about stalks and stuff as well. Alright, let's do it. Basically, so stalks are a way of thinking about sheaves locally. So let's do definition. So, a germ at P is an object of the form so firstly we're going to have F and some open U, where P is in U and F is a section over U. Okay, so that's what a germ at P is, and the stalk at P. Oh shoot, yeah. Modulo the following equivalence relation that I'll do this in purple. Yeah, modulo the equivalence relation that if Fu is equivalent to GV, if and only if we have it that Fu is equivalent to GV, if and only if we have it that, that we can find some even smaller neighbourhood upon which, if you restrict them to that neighbourhood, they agree. So, such that res U V of F is equal to res V W, where W is some even smaller subset. Okay, and a stalk at P, which we'll denote by FP, or, OP or whatever. A stalk at P is a collection of germs at P. And of course, if, we're talking about rings, then this will be a ring, and so on and so forth. However, because there is a natural map from some O of U to FP. Sorry, not O of U, FU. Sections of U, sections over U to the stalk at P. The stalk at P can also be thought of as a colimit. And actually what it is the following colimit. FP is equal to the direct limit of all of these F of U's, where these open sets are things containing P, basically. So that's what the stalk is. You can think of it like that too. And sometimes, again, this universal map, if you draw out the colimit, is useful about proving stuff. It's useful with regards to proving stuff about this stalk. Okay, so I might as well give some examples now that I've covered what I want to cover in terms of theory and stuff. So yeah, okay, let's see some examples. So firstly I should give an example of a pre-sheaf that's not a sheaf. And for that we'll do bounded functions over C. Bounded functions over C. Why is this not a sheaf? Okay, so it's clearly a sheaf. A free sheaf. Let's not go over that. But why is it not a sheaf? The reason is it doesn't satisfy the identity axiom. It might not even satisfy. Let's see. It might not satisfy the gluability axiom either. Hold on. Let's see. Let me just think about this. Does it satisfy the gluability axiom? I don't think it does actually. Maybe it might even be the case that it satisfies. Yeah, it satisfies the identity. Or maybe it doesn't, but the counterexample I'm thinking of doesn't satisfy gluability. Because if we define some f of x equal to x, this is bounded on some open cover which we can pick. This function here is bounded on ui and uj, and they'll agree on the overlaps. There will be x on the overlaps. If we just define f of x equals x on ui, and we have f of x equals x on uj, then on the overlap they'll agree, but there'll be no bounded function in the sections of over u. There'll be no bounded function such that the restriction, because the identity is not bounded in general, so it doesn't work there. You can't glue them and make another unbounded function, basically. That's why it's not a sheaf. So I do think it's important that if you have, say, one thing is kind of like another thing plus some extra axioms, it's probably always good to have that, basic example to fall back on, where you have an example of one thing, in this case a pre-sheaf, that does not satisfy the extra axioms. Okay, but let's look at something that does satisfy the extra axioms. And this is called the constant sheaf. So the constant sheaf, so for some set S, denote the constant sheaf by this. So it's S underlined, basically. And how it's defined it is, you give S the discrete topology, and then each section is a set of continuous maps from U to S. That's what each thing is. That's what the constant sheaf is. And I have a funny suspicion that we will be using the constant sheaf quite a lot. So basically it's just, kind of locally constant functions. So I do believe that constant functions do fail, but locally constant ones won't, so. Okay. In general, actually, if we take another topological space y and define each sections over u as continuous functions from u to y, then that will work as a sheaf too. And so this is just a special example. And yeah, that's just a special example. Continuous functions over R, which I believe is either similar or precisely the motivational example that Vakil gives is another special example. And so, actually, yeah, I'll write that down because that's quite a good example, actually. So, given any topological space, given a space Y, given a space Y, if we define f of u to be set of all continuous maps from u to y, this is a sheaf. Alright, so that's quite an important example, actually. Now, one thing which I will hopefully be mentioning in next video is the étalé. Definitely butchered that pronunciation. Étalé perspective on a sheaf and how to define it like that. It's quite interesting. I looked at it briefly and it's giving me very algebraic vibes to it, so I'll definitely try and include that in the next video. The last thing I looked at is the pullback of a sheaf, and basically that the push forward a sheaf is a sheaf. But I'll leave all of that to next video. I'll just leave this video as being definitions of a sheaf, a couple of the good examples, and some stuff about stalks and so on and so forth. Nothing too strenuous. And hopefully I'll go on to some more kind of technical details about sheaves, and maybe go on to some stuff about morphisms of sheaves. That's what I'm aiming to do. But then again, I can't raise my hand and say, "Miss, don't give me homework," because I'm learning about morphisms of sheaves. That would be pretty cool, but okay. So yeah, I'll just do as much as I can, really, and yeah, hopefully you find this series somewhat helpful, or you can help me during the series by sharing tips for learning algebraic geometry or whatever. So yeah, I'm just going to be continuing with sheaves next video, and that's it for this week. Goodbye. Oh yeah, also congratulations to Usyk, who has successfully become unified heavyweight champion of the world. Yeah, congratulations to him.